Hello everyone, my name is Rzeszutek. I'm a third-year PhD student at the University of Manchester, where I work on protective marine coatings based on zinc. My today's presentation will be focused on the influence of zinc loading in epoxy zinc primers on steel, on the efficiency on the transfer of galvanic current during cathodic protection mode delivered by zinc dust in these paints. To begin, I will make a short introduction about zinc-rich primers. I may need to repeat some of the things that you have heard during Isahak's presentation, but I need to repeat them to make it easier later for me to describe and explain the results that I have obtained in my research work. This will be followed by a very brief description of materials, 5 types of coatings that are included in my PhD project. And then I will move on to the results section, which includes open circuit potential measurement results and the Anodic Potentiostatic Polarisation test results. The presentation will be focused on the Anodic Potentiostatic Polarisation test, the methodology behind this test, and information it can provide us about the performance of zinc primers on steel. So typically, zinc-rich primers are comprised in the first layer of a 3-layered coating system and remain the weakest point of that system. Due to very high zinc loading in these coatings, which is at least 88% of zinc dust, they feature very high level of internal porosity and poor adhesion to the steel substrate. Such a high zinc loading in these coatings is necessary for the development of electrical continuity between zinc particles in the coating and the steel substrate, so that once the coating is fully penetrated by the electrolyte, or the steel or the coating system is damaged and the steel is in contact with a corrosive medium, the zinc can corrode sacrificially to galvanically protect the steel. This mode of protection is known as cathodic protection, and it's known to be the main mode of protection delivered by zinc dust in the paint. Cathodic protection is finite, however, since as zinc has been corroding for a certain period of time, the electrical continuity diminishes. Also, zinc corrosion products precipitate and build up on the surface of zinc particles and polarize them. But despite the changes that develop in coating structure, the substrate is still protected, but the cathodic protection is taken over by post-cathodic protection, which is most often attributed to the barrier and inhibitive properties of zinc corrosion products. Zinc-rich coatings, zinc-rich primers are a well-established method for the protection of offshore steel structures against corrosion since 1960s. However, rising environmental concerns with regards to the toxicity of zinc that is released to the seawater during its corrosion process, as well as cost pressures, stimulate the reduction in the quantity of zinc in these coatings. Another industrial challenge is the necessity for the development of low solvents, high solids counterparts of conventional coatings, which is driven mainly by the increasing restrictions towards the emissions of volatile organic compounds during paint production and application. In response to these challenges in my PhD project, I have been studying 5 different epoxy zinc primers on steel. They comprise 4 low solids formulations with 4 different zinc loadings, with the highest one representing standard conventional zinc-rich primer, which is known for its excellent anti-corrosive performance, both in the open circuit potential measurement, as well as in the accelerated corrosion testing. The last formulation is a high solids version of the standard zinc-rich primer, which is produced with basically the same zinc loading. All coatings that are included in my PhD project are produced with the same pigment volume concentration, which in the case of the coatings with reduced zinc loading is maintained by addition of extra talc. The first measurement that I performed on these coatings was, of course, the open circuit potential measurement, which was carried out with the aim of estimating of the duration of cathodic protection delivered by every coating type. And in the case of the epoxy zinc primers of steel, the cathodic protection is defined as a period of time during which the free corrosion potential of coating sample is in between the value of the free corrosion potential of zinc and steel. And those, of course, as we are able to see, the longest duration of cathodic protection in the case of scribed coatings is achieved for the coating with the highest zinc loading with 44.5 volume% of zinc and lasts for 16 days, whereas the shortest duration of cathodic protection is delivered by the coating with the lowest zinc loading, that is 22.3 volume% of zinc. What was very characteristic was that in the case of the high solid coating, I measured no cathodic protection since the value of the free corrosion potential of coating sample exceeded the value of the free corrosion potential of iron from the very beginning of open circuit potential measurement. And when looking at SCM images of these coatings after the anodic potentiostatic polarization test, we are seeing activation of zinc in the entire coating cross sections in the case of coatings with two highest zinc loadings. There is increasingly limited activation of zinc in the coatings with reduced zinc loading and no activation of zinc in the case of the high solids coatings. In the case of the high solids coatings, we are also seeing a crack progressing along with the metal coating interface, indicating detachment of that coating from the steel substrate, which disturbs the adhesion and prevents the zinc from providing galvanic protection to steel. Now, I would like to move on to the main part of this presentation, which is the anodic potentiostatic polarization test. In this test, I have polarized all coatings at the value of the free corrosion potential of iron. By doing this, I wanted to create the degree of changes that are developed in the coating structure at the end of the cathodic protection mode. As you are able to see in the first row, there are 4 plots for all 4 low solids formulations, and all of them show similar trend. The initial increase of current results from the progressing penetration of the electrolyte and activation of zinc for sacrificial dissolution, and it's followed by subsequent decrease, which comes from the progressing loss of electrical continuity between zinc particles in the coating and the steel substrate. Simultaneously with the anodic potentiostatic polarization test, I carried out electrochemical impedance spectroscopy at regular time intervals to study the changes of polarization resistance that occur in the coating throughout the duration of the polarization process. And the changes of polarization resistance are portrayed in the third row, in the plots shown in the third row in the form of pink plots. So what's very characteristic for all these coatings is that the peak of current, which indicates the point at which most of the zinc in the coating is activated for sacrificial dissolution, corresponds to the lowest value of the polarization resistance of these coatings is achieved at the same time when the peak of current, which again indicates maximum activation of zinc for its sacrificial dissolution. Then I studied the changes of the peak of current and the lowest value of the polarization resistance that were measured for these coatings as a function of zinc loading. I will describe this graph in more detail shortly when I will be comparing the data obtained for the intact coatings with those obtained for scribed coatings tested in a scribed form. Here we are looking at the data obtained for scribed coatings. As you are able to see, the trend of changes looks exactly the same as for those coatings when they were tested in an intact form, but the values of current measured are significantly higher. The changes of polarization resistance show exactly the same trend as for those coatings in an intact form, but again, the lowest value of the polarization resistance measured for these coatings is significantly lower. So when we compare the changes of the peak of current measured for all those coatings in both intact and scribed forms, we can note that as we move on from the coating with the lowest zinc loading to the 29.7 and 37.1 volume percent, the peak of current increases by 10 orders of magnitude. And at the same time, the lowest value of the polarization resistance decreases by 10 orders of magnitude. And this is the case for both intact and scribed coatings. However, for any given coating tested in an intact form, the peak of current measured during polarization process is 10 orders of magnitude lower than for the same corresponding value for the same coating tested in an intact form. And on the other hand, the lowest value of the polarization resistance for coatings tested in an intact form is 10 orders of magnitude lower than the corresponding value measured for those coatings tested in a scribed form. This indicates that the zinc in epoxy zinc primers, when they are tested in a scribed form, is activated a lot more faster, a lot more efficiently in coatings with a scribed form, and hence the larger values of current and lower values of the polarization resistance measured for these coatings in a scribed form. I used the anodic potentiostatic polarization data, which show the trends of changes of, as I said earlier, current versus time to estimate the amount of charge that passes during sacrificial, accelerated sacrificial dissolution of zinc. And by doing this, I could estimate the mass of zinc that dissolves from every coating type during this accelerated testing. As expected, the largest mass of zinc measured that has dissolved sacrificially for coatings tested in both intact and scribed forms is measured for the standard zinc-rich primer with the highest zinc loading, which exceeds significantly the mass of zinc dissolved from coatings with reduced zinc loading. However, what is very interesting in these results is that the overall amount of zinc that has dissolved sacrificially during anodic potentiostatic polarization test from coatings in a scribed form is smaller in percentage, it's lower in percentage compared to the mass of zinc that dissolved from these coatings tested in an intact form. This is explained due to the different ratio of the cathode and the anode surface areas that are exposed to corrosive medium. So in the case of the scribed sample, the ratio of the steel to zinc, the ratio of the surface area of steel to zinc is a lot larger than in the case of the intact sample, which results, as I said earlier, also when describing these plots, this leads to very fast and rapid activation and sacrificial dissolution of zinc. This in turn results in a sudden fast loss of electrical continuity between zinc particles in the coating, and therefore less overall amount of zinc that is used up for the sacrificial dissolution, for the cathodic protection. In the case of coatings tested in a scribed form. And this is important considering that it seems that the extent of damage in the coating or in the coating system may affect the extent to which zinc as a galvanic, as a sacrificial pigment is used during its galvanic activity, throughout the cathodic protection mode. When looking at SCM images of these coatings after the anodic potentiostatic polarization test, we are seeing similar type and degree of changes that develop in coating structure as to those that we can see we looked at earlier after the open circuit potential measurement. There is activation of zinc in entire coating cross-section in the case of both coatings with the highest zinc loading, and limited activation of zinc in the case of coatings with reduced zinc amount. Now I would like to very briefly discuss another case in which a standard low solids zinc-rich primer has been compared against its high solids counterpart. The anodic potentiostatic polarization test of the high solids coating did not yield the curve showing positive current resulting from the sacrificial dissolution of zinc, which indicates that in the case of the high solids coating, there is no cathodic protection, as opposed to all low solids formulations that I have discussed earlier. Also, when looking at SCM images, we are seeing this crack progressing along the metal coating interface, which disturbs the adhesion and prevents the zinc from providing galvanic protection to steel. And this reinforces what we have learned about this coating during the open circuit potential measurement. So to sum up, anodic potentiostatic polarization test has been proposed to study the changes in the polarization resistance, changes in the transfer of galvanic current, as well as the differences in the mass of dissolved zinc from 5 different formulations, which included 4 low solids and 1 high solids epoxy zinc primers on steel. It seems that the extent of coating damage and the ratio of the anode and the cathode surface areas that are exposed to the electrolyte or corrosive medium affects the extent to which the zinc as a sacrificial pigment is utilized during cathodic protection mode. And this test can be used to compare the galvanic activity of pigments in performance coatings. It can also be used to study the differences in galvanic activity of coatings based on mixture of pigments, as well as to study how different formulation components, such as binder systems, which I have briefly described in the previous slide, influence the performance and the utilization of sacrificial pigments and their galvanic activity. At the end of that presentation, I would like to express my deep gratitude to my supervisors, Professor Stuart Lyon, Doug Beaumont, Chris Johns, and also Simon Gibbon. I would like to give my special thanks also to the University of Manchester, Akzo Nobel, and DPSRC for funding of my PhD project. Thank you very much for your attention.
Thanks, Cassia. Any questions for this speaker? I shouldn't really ask any questions because she's my student. So it's,
yes, I couldn't read some of your graphs, so I couldn't get a clear idea of your current densities. What's the maximum current density you're getting from the coated samples?
In the case of intact coatings, the highest current density or value of the current was measured obviously for the primer with the highest zinc loading, and it was about 700 microamps per square centimeter.
Microamp centimeter. Yes. Okay.
Yes.
That's quite a high current density, isn't it? Okay. So yes. I don't understand why the scribed sample is giving you more current than the unscribed sample, which is what I understood you to say. Maybe I've misunderstood.
That's the case. The measured current in the case of scribed sample was about 2000 microamps. But the surface area of that sample was also larger. So in the case of intact sample, the surface area was 1 square centimeter. In the case of scribed sample, this was 7 square centimeters, but there was very large scribe that I applied. It was 1 centimeter long and 2 millimeters thick.
So, okay, so you're not comparing apples with, you're comparing apples with oranges, so to speak, in the sense they're not the same.
They are not the same.
If you look at it in terms of current density, what would you conclude?
I do not represent this data in a form of current density. I only represent this data in a form of peak of current. The reason why I decided not to represent this data in a form of current density is that that could be done in the case of the intact sample, because I could assume that the rate of zinc dissolution from entire surface area of the coating is the same. But this is not the case in the case of scribed sample, since I think I can assume that the rate of zinc dissolution on the walls of the scribed in the vicinity of the defect will be a lot faster than somewhere further from the defect. That's why I did not represent
Okay, I
anything.
mean, you end up with a slightly confusing conclusion by doing that, I think, but I understand what you're saying. So if you put two scribes on, you would get twice the current?
I wouldn't say that would be twice current, but perhaps even higher.
But it'd be interesting because you'd be able to decide then how much of the current was coming from the scribe and how much was coming from the surface. I mean, you may be able to do that anyway because you compare the scribed with the unscribed.
I was thinking of doing that. I mean, I wish I had more time, then I would also create defects of different sizes or multiple defects to measure this, because I don't think the changes would be linear, proportional, but it would be interesting to observe how different size of the defects or how multiple defects what results they would yield, basically.